Hey guys, today we're going over a basic introduction to the concept of equilibrium. So what is equilibrium? In a chemical sense, equilibrium is when you have a reaction that is going forward and creating products at the same rate that those products are decomposing or recreating the reactants they're made from. And so whenever we look at a equilibrium, we end up having the same amount of material in the equation, and whenever it reaches a certain point, that material is still going to be moving, it's still going to be reacting, it's just that the rate of reaction is going to be the same as the rate of the reverse reaction. So looking at the previous unit of rate constants and mechanisms, if we have a forward rate, let's say A plus B, and we have a reverse rate, D plus E, then we can create an equilibrium of A plus D is at equilibrium with D plus E. Now, each of these sides is going to have a specific rate. And so if we divide the forward rate by the reverse rate, we're going to get a constant, K, the equilibrium constant. And we can do this with rate, we can do this with molarity, and we can do this with partial pressure. So essentially, if we start out with A plus B is D plus E, then we can calculate their equilibrium molarity, or using their equilibrium molarity, if we take the concentration of the products D and E put to the power of their coefficients, and we divide that by the reactants molarity put to the power of the coefficients, we get an equilibrium constant for the concentration. We can do the same thing with partial pressure in terms of gas equations. So if we take the partial pressure of the products D and E to the power of their coefficients, and we do the same thing with the reactants, partial pressures of A and B put to the power of the coefficients, we get a similar concept. We have a constant for pressure. So let's look at a popular example. If we look at the Haber process, this is the manufacturing of ammonia. We can see that nitrogen gas and hydrogen gas are at equilibrium with ammonia gas. So looking at their concentration, if we have the concentration of the product, ammonia, squared, because we have 2, we divide that by the molarity of the reactants being N2 and H2 cubed, because we have 3H2, we get a constant. We could do the same thing if we were given the partial pressures of these gases. We could find the constant for pressure. And we could even do this if we were given some pressure and some concentration. Essentially, we can relate these two concepts with the ideal gas law. That being that if you have Kp, that's going to be equal to Kc times RT to the delta N. So by that, I mean that the constant for pressure is going to be the same as the constant for concentration multiplied by R, that being our gas constant. In this case, we're using atmospheres of pressure, so it'd be 0.08206. And our temperature is going to be in Kelvin, so add 273 to whatever Celsius is given. Now, delta N is the main new part. So delta N can be described as the overall change in moles from reactants to products. So if we take, in this equation, we take D plus E, and we subtract A plus B, that's going to equal delta N. In the case of ammonia, that'd be these two minus these 3 plus this 1. So our coefficients are going to end up giving us a -2 in that delta N spot if we were to try to convert the pressure to concentration of the ammonia process. Now, in terms of interpreting what these constants mean, if we look at simply the value of the K, then we can determine whether or not a reaction is going to end up favoring the products or the reactants. Essentially, is this going to be an effective process for creating products, or is very little going to happen and we're going to be left with a bunch of reactants? Now, in the case of K, temperature plays a big role and is going to affect the equilibrium. And in the case of the Haber process in creating ammonia, we've learned to manipulate the different constants in order to favor the reactants less than we favor the products. So if we do a K value that is greater than 1, that means that we have more products in terms of concentration or pressure than we do reactants, which means that our equilibrium favors that. If we have the opposite, we have K is less than 1, then we're going to favor the opposite. We're going to be favoring the reactants because we have more reactants on the bottom. It's going to lead to a smaller K value. So we're going to be valuing the left side of the equation, the reactants. So moving on to a practice problem, let's go to problem 15.13 of equilibrium, looking at the equilibrium constant. So let's suppose that we are looking at a gas phase reaction where element A converts to element B and element B converts to element A. Both of these will assume our elementary processes with rate constants of 4.7 times 10 to the -3rd, s to the -1, and 5.8 times 10 to the -1st, s to the -1. These are the rates for the forward and reverse reaction. Take a second and decide what you would do in this equation and what answer you would get. So for this equation, we're going to simply divide the forward reaction by the reverse reaction, and that's going to cancel out this per second, which is common with these constants, is that they have no value. They have no units attached to them. There's simply a constant. And so in this case, that constant is going to be 4.7 times 10 to the -3rd divided by 5.8 times 10 to the -1st, which is going to end up with 8.1 times 10 to the -3rd. So the second part of this problem, part B, asks us which element is going to be favored, which one has higher partial pressure. Looking at K, is it greater than 1 or less than 1? Looking at K, it is far less than 1, which means that element A is not going to lose much in terms of pressure or concentration. It's going to remain favored by the equilibrium. We're going to have more of element A than is going to be decomposed into element B. Try a couple of problems on your own going through the sections 15.1, 15.2. They're very straightforward because essentially starting out with this unit, a lot of information is given and not very much needs to be derived. We can use the original two equations of Kc and Kp are simply products divided by reactants, and make sure to put them to the power of their coefficients. That's all for this lesson. A very basic introduction, and I hope this helped.